Hi, and welcome to UNSW, the School of Mathematics and Statistics. My name is Thomas Britz, and I'll be looking at problems 42 and 44 from the course MATH3411. And in this problem, we have to look at the sources from question 29, 33 and 35. Back in those questions, we had to calculate the Huffman code and look at the average length of it, which was minimal as we know. Here we have to calculate the entropy of these probabilities and also calculate the Shannon-Fano code, which is a different coding. In some ways a little easier to encode, but yeah, it's a bit different from the Huffman coding. And we'll be looking at the average length of these codes as well, and then comparing the entropy and the average code word lengths of the Shannon-Fano code and of the Huffman coding. So let's begin. To calculate the entropy, all we have to do is just calculate a simple sum of terms, and they depend on the particular radix. Here radix is 2, so we're looking at the entropy base 2 of these probabilities. And that's given by this sum here, minus the sum of the probabilities times the logarithm of those probabilities, base r, and here r is equal to 2. So we just calculate. So minus the first probability is a half, so a half log 2 a half, that's just a half, minus a third log base 2 a third, and then minus a sixth log base 2 a sixth, and that roughly gives us 1.46. So that's our first answer. Now, if we compare it to the average length of a Huffman code and see what that number is in relation to that, well, we could refer back to this problem and its answers for the Huffman coding, but we could quickly do it here too. So if we were to use Huffman encoding, we can quickly do that. If we add the two smallest probabilities here, which are written down in order, we get a half. There we go. And here we go. So the average length here is just the sum of those two, and we have that average length of the Huffman encoding is equal to 1.5. And that, as you see, is a little bit bigger than the entropy, and that's always going to be the case. So here we can tidy up a bit. So now to calculate the Shannon-Fano code, we look at these probabilities and we order them again in order, like so. So these were the probabilities pi. Now, what we do with these pi's to calculate this code is very simple. First we can draw a little table here. Let's do that. First we just invert the probabilities, so pi. So that gives us 2, 3 and 6. Next we calculate the code word lengths. So it's sort of back to front compared to the Huffman coding, where we first found the code words which gave us the lengths. Here we first find the lengths, and that will give us the code words. And the way that we do that is that we see, well, here's the radix 2, so we're looking for a number here so that 2 is less than or equal to 2 to the power of that number here, li, well, L1, the first one here. So this number here is that inverted probability, and we just have to find some number there which will satisfy this equation. And of course, if we put a 1 there, then that will work. So we have a 1 there. Next, if we want to find the length there, we have to do the same thing, except instead of 2, we have 3. So 3 is less than or equal to 2 to the power of something. And the smallest something is just 2. So we have 3 is less than or equal to 4. And that'll work if we have the exponent or the power 2. Finally, we have 6 is less than or equal to 2 to the power of 3 or anything above, so the smallest power there is just 3, and there we go. Now we've found all the lengths of the code, and at this point we could calculate the lengths, the average lengths, so that will give us some number. If we take these probabilities, a half times 1, a third times 2, and a sixth times 3, in fact it'll give us 5/3, which is roughly around 1.67. So you see that the Shannon-Fano, the average length of the Shannon-Fano code is greater than the average length of the Huffman code, which we've proved to be minimal in that sense, which again is bounded below by the entropy here. So we've got a sequence of inequalities, and of course these are strict, but we can write them up. And these are all going to be also less than or equal to the same entropy plus 1. And that's one of the theorems that we saw in chapter 3. So now all we need to do is actually find the code words for the Shannon-Fano code. So let's do that. We have some code words to find. And the way that we do that is just to draw up a decision tree, like we've been used to doing. And the way that we do that is just do it by the standard form, starting at the beginning of the tree and filling up as we go along. So first we need a code word of length 1. So here we have our decision tree branching first off into 0. And there we have our first code word, 0. Now we need a code word of length 2. So we're branching down here and then branching off into 0 first. So that gives us a code word 1, 0. And finally we want a code word of length 3. So we can use the next branch here, 1, and then off into 0 again. So that gives us 1, 1, 0. And we're done. So this is the encoded word. So the code word with probability 0 gets the code word 0, and then we have a 1, 0 and a 1, 1, 0 for the other two code words, and we are done. So here were the two things that we have to find, but we also had a bit of extra information given by comparing these code word lengths. So now let's look at the probabilities that we saw in question 33, and this time it'll be with radix equal to 4. Everything's going to be pretty much the same, but there'll be just a little bit of difference in the construction of the Shannon-Fano code and also in the calculation of the entropy. So let's start with the entropy. So as before, it's equal to minus the sum of the probabilities times their logarithm. But now the logarithm is base r, which is equal to 4, so it's base 4. So we have that it's minus 0.22 times the logarithm, base 4 of 0.22, and then a whole lot of terms, ending up with the last term, 0.02 times the logarithm, base 4 of 0.2, and this is roughly around about 1.38. So that's the entropy. Now, the average code word length of the Huffman code that we found in question 33 was exactly equal to 1.47. And you can see that this number here is bigger than 1.38, which is as we want it to be. We want this number to be less than or equal to this number, which is hopefully less than or equal to this number as well. So let's just clean up a little bit. So we have that the entropy was roughly 1.38. And the entropy here and this average code word length of the Huffman code, they're not too dissimilar. This is quite close to the bound given by the entropy. The Huffman code is optimal in the sense that it's got the lowest average code word length, but that's only in the sense that we are encoding one symbol at a time. If you're allowed to use more information, and in particular if you're allowed to encode extensions of the code, then you can actually achieve this bound well, in the asymptotic. So, what else do we have to do? Well, we could find the average code word length of the Shannon-Fano code. So let's do that. To do that, we do like before. We write down the probabilities, PI, and here they are. So 0.22, 0.20, 0.18, 0.15, 0.10, 0.08, and 0.05, and finally 0.02. Now we want to find the inverse probabilities of these numbers, or the inverse of these probabilities, rather. So let's write up a little table as before. And here we have roughly 4.5. Here we've got 5. This is roughly 5.6. Roughly 6.7. This is 10. This is 12.5, 20, and 50. So these were the inverse probabilities. To find the lengths, now we have to ask, well, for instance, to find the first length here, we have to ask, well, 4.5, or roughly about 4.5, can we find something that's bigger than this if we look at powers of 4? So 4 to the power of 1 is not enough, but if we raise it to 4 to the power of 2, then we've got 16 there, which is, sorry, which is bigger than 4.5. And so this 2 here will be the length. Now 16 is also bigger than 5, or bigger or equal to 5, 5.6, 6.7, 10, and 12.5. So for instance, it's still bigger than 12.5. So this 2 here will be the lengths in each of these places here. Now if we have 20 on the other hand, then this inequality no longer holds. We have to have a bigger power than just 2. So let's go 1 up to 3. So now we have 64 is greater or equal to 20. So 3 there. And, well, 64 is also greater or equal to 50. So we have the 3 there, and we're done. So now we've found the code word lengths. So this is sort of back to front with compared to the Huffman coding. And we can then find the average lengths of the Shannon-Fano code, just to be the weighted lengths here, weighted by the probability, so 0.22 times 0.2, sorry, times length 2, plus 0.20 times 2, and a whole lot of other terms, concluding with the term 0.02 times 3. And this roughly gives us an average, or a number which is roughly 2.07. So that's our average code word length. And that is in fact bigger than the average code word length for the Huffman code, which in turn is greater or equal to the entropy. And this is also less than or equal to the entropy plus 1. So, sorry, this should be a H. We're talking about the entropy now, plus 1. So we have all of the inequalities from the theorem intact. They do hold. Okay, so now all we need to do is find the actual code. So we've got the lengths, and using these lengths, we just have to construct the code using the by drawing up a decision tree, just in the standard way. So let's do that. So here we're looking at radix 4. So at every node we have up to 4 branches possible. We're going to do it in the standard way. So we just take the very first available nodes. So 0 and 0 for the first one, for instance. That gives us 0, 0. So if we have the code words in this column here, Shannon-Fano code words, then the first of these is 0, 0. And in fact we can choose 4 of the nodes here, branching off from this node. So we have 1, 2, and 3. And the code words that we get are 0, 1, 0, 2, and 0, 3. So now we've got 4 of the code words. We're halfway. Now to get the next 2 code words of length 2, we can't use that node, so let's go on to the next one, which is 1. And there we can go on to 0 and 1. So that would be 1, 0 and 1, 1. And finally, whoops, there we go. And finally, to get the last 2, they have length 3. We can continue from this one down to the 2 node, and from there go to 0 and 1. So we have 1, 2, 0 and 1, 2, 1. So 1, 2, 0 and 1, 2, 1, and we're done. Because these are our code words, the 8 code words that encode each of the symbols for the 8, or that are implicitly stated there by their probabilities, and that's it. So thank you very much.